1.3, Continuity, End Behavior, and Limits. In this section, we're going to continue describing functions with rich language and work on our math vocabulary. So the first thing we need to worry about is this idea of smooth and continuous for a function. So smooth would be a function like this. So there are only smooth rounded curves. The graph has no sharp corners. So this is going to be smooth. If you contrast that cubic function with an absolute value function, the absolute value function is definitely not smooth. It has a sharp corner. The other word we're going to use to describe functions is continuous. So continuous means the graph has no breaks and can be drawn without lifting the pencil. So again, if I go back to some kind of polynomial function, I can draw the whole thing. I have to put my little arrows at the end after the end, but I'm doing the whole thing without lifting my pencil up. So let's think instead if we had a function like this, where I have part here, and then I go over here and do my second part of the graph. That would be like a reciprocal function or some kind of rational function in general. So that's not going to be continuous. The other one that comes to mind right away would be a piecewise function, where I have part of my function over here, and then it jumps, and then I have the other part of my function. So that would not be continuous either, because I have to move my pencil. I have to lift it up and move it. Let's label this one continuous. I always like to give you guys a picture of what we're looking at. Here are our types of discontinuous functions. So the first one is infinite discontinuity. So the reason we call it infinite is because on this asymptote, x equals 4, I have this part of my graph is going off to infinity by that asymptote. It's not actually going to equal 4. X will not actually equal 4, but it'll get closer and closer to 4, and y goes off to infinity. And then same thing over here on this part of the graph. It's getting closer and closer to 4 for your x, and your y is going to negative infinity. So that's why we call it infinite discontinuity. I have a piecewise function where I jump from one point to the next, which is why I call it jump. And then the last type is removable discontinuity. And that's because if we remove the whole, it would be continuous. For the first problem, we're going to be determining whether the function is continuous at the given value. So the math for these problems is not very difficult, but again, we've got to think about everything we know about functions, how they work, what the shape is, what things look like. We really have to have a lot of knowledge to be able to do problems like this. So what I notice about f of x is I have an x squared, I have 3x, I have 1. My highest power is x squared. That means I've got a quadratic, which means if I graph it, I have a parabola. And because the 4 is positive, I would have a parabola that looks like this. So we can already tell that the graph is going to be continuous at any value of x along this. So I'm going to say yes, continuous. Often, if it is continuous, you will be asked to find the value of the function at x. And so I am going to go ahead and just find f of negative 2 as well. So that means I would be finding 4 times negative 2 squared minus 3 times negative 2 plus 1. Let's see, 4 times 4 plus 6 plus 1, 1. 16 plus 6 plus 1, so 23. So it's continuous, and at negative 2 it equals 23. So for B, what I notice is that I have a piecewise function. So I have this part of the graph here for when x is greater than 3. And then if x is less than or equal to 3, I have the part of the function that says x minus 5. So we have two different pieces to our piecewise function. So what I know about piecewise functions is that this number that we use for the inequalities, it says greater than 3 or less than or equal to 3, that's where that jump can happen. So the jump that we would see when we jump from one value to the next is really a jump in y values. So what I need to do is I need to substitute 3 into both of those parts of my functions, even though this just says greater than 3 and not equal to. I'm still going to plug it in there. And I want to see, because there'd be an open circle at whatever 3 was, I need to see if there's a jump in those y values. So first we'll do 2 times 3 plus 1, which is 6 plus 1, which is 7, and then 3 minus 5, which is negative 2. So I can clearly see I have a jump between those two y values, and so I would say no, and we have jump discontinuity. So again, the math I am doing is not difficult, but I really have to bring a lot of knowledge about graphing and about functions to what I do with these math problems. On my last one, I have a rational function. So with rational functions, I'm always trying to get a good idea of all the different factors and what's going on. So I would definitely factor this before I do anything else. And then when I factor it, I notice they both have a factor of x minus 2. So whenever we have a factor in common, that creates a whole. And because 2 minus 2 would equal 0, the whole is at x equals 2. So my function can really simplify down to f of x equals 1 over x plus 2 for graphing purposes. But I have to remember that x cannot equal 2, and so it creates a whole. So this is like that part of the domain before when we would have to worry about x not equaling a certain number. I still have an x plus 2 here in the denominator. That means x equals negative 2. We can't have that either, but that's actually going to create an asymptote. So it's only when something cancels out that it creates a whole. So this would be, to answer our question again, no, it is not continuous. And we have removable discontinuity. So if this function had asked us what happens at x equals negative 2, because that's where our asymptote is, at x equals negative 2, we would have infinite discontinuity. So that's just kind of an extra little thing. So we're looking at all those different types. The intermediate value theorem. So if you look this up in your book, it's super confusing. They use a lot of letters and a lot of language. The idea, though, is really very straightforward. So I'm just going to do a quick graph. I will draw my axes first in black, and then I'm going to draw some kind of a smooth curve, and we're going to make 2 points on our graph. I'm going to space them really far apart, but that's okay. They don't have to be far apart. They could be really close together. This first one I'm going to say is where x equals a. So then my y value would be f of a. So that just means the y value that's associated with a, right? The function of a. This one I'll call b, and so my y value will be f of b. So those are my ordered pairs. So this idea for the intermediate value theorem is that if f of a and f of b are, and I better write an if here, are opposite in sign, that means one's negative, one's positive. If they're opposite in sign, so if one is positive, one's negative, or the other way around, that means there must be a 0 between them, because zeros happen when we cross that x-axis. So we have to have a sign change in y. So if they are opposite in sign, there is a 0 between them. We really should say at least 1. At least 1. Because you see from the graph that I wrote, there's really 3 between them. So if we go from a positive to negative, we have to cross the y-axis. It is impossible to make a function where we go from up here to down here and not cross the y-axis. If it's continuous, there's got to be a 0 between them. For problem 2, we're going to determine between which consecutive integers the real zeros of the function are located on the given interval. So this is a really loaded problem. So they're giving us an interval, -3, 2. So -3, 2, if I think about all those consecutive integers, and hard parentheses means I start with -3. The consecutive integers would be -3, -2, -1, 0, 1, all the way up to 2. So we want to know between which consecutive integers, so consecutive would be 2 in a row, the real zeros of the function are located. So in order to tell if I have a 0 between two x values, I really need to find the y's, because the y's are the part that I've got to look at for that change in sign. So I'm going to need to find f of -3, f of -2. We're going to have to find all of them. So I will start and I could do regular substitution, but I'm going to choose to do synthetic substitution because it's a good review. So I put -3 in the corner, and then next to it I write down the coefficients of my function. I have a 1x cubed. I have no x squared, so I have to put a 0. 2x, so I write a 2, and then 5. So the way I start my synthetic substitution, synthetic means fake. I'm not really substituting the -3 into this function. I'm using this other fancy cool method, and I get the same answer. I'm going to bring 1 down. Then I multiply it by the -3, write it underneath the next number, and then I add. After I add, I multiply it back again. -3 times -3 is +9. And then I add 11 times -3 is -33. And I add one more time. So this last number that I end up with, that is the value of f of -3. So synthetic substitution is a really cool shorthand way for us to figure these out. Now I'm going to go ahead and do -2. Again, we bring down the 1, multiply it back, add them, multiply it again. You get pretty fast at it when you do a lot of these. I want to check -1. Okay. And oh, it looks like I have a sign change, so there's a 0 there. I'm going to keep going in case there's any more. Whenever I'm evaluating 0, I can find that right away. I know that f of 0, that's always going to be the value of the constant term. If I put zeros in for my x cubed and my x, I'd be left with 5. So no sign change there. We'll go ahead and try 1. Now something's happening here. I'm noticing that because there's no minus signs, I am just getting bigger positive numbers. And I know the next thing's going to happen as well, so there's no point in me checking any more values. I know 2 is just going to yield a bigger positive. So I know that the 0 is, let's see, it would be between the -2 and -1. Or we could write it as an interval, -2, -1. I guess we could write it that way as well. But that's where our only 0 is going to be for this function. It's between -2 and -1. End behavior. So when we talk about end behavior, we are really looking at what is going on with our y's. So let's write this as what is happening with our y's, or what are the y's doing? As x goes to the right and left. So if I looked at a quick example here, I'm going to go back to that cubic term or cubic polynomial I keep using. And by left, I would mean this part over here. So when I think about my graph, I want to go as far left as I can. That's the left. So that would be, if I'm talking about the left, is that's x goes to negative infinity. And if I think about a number line with 0 in the middle for x, out here to the left is negative infinity, to the right is positive infinity. So that's what we're doing. We're looking at what happens as x goes all the way to the left to negative infinity, and as x goes to the right to positive infinity. And as we go to negative infinity, we're thinking about the limit of our function. So limit of f of x. Sometimes they'll just say x goes to negative infinity, f of x goes to, they'll write it that way. So that's kind of the way we did it in Algebra 2. This year, we're going to be writing it as a limit instead. So what does that equal? Well, this graph is going down. And so as x goes to negative infinity, so is y. On the other side over here, if my graph is going up, as x goes to positive infinity, my limit of f of x, since it's going up, is going to be positive infinity as well. I usually say positive infinity, just trying to differentiate from negative so you're very clear on what I mean, but I don't write the positive sign. It's not necessary. So we're going to look at an example now, and I'm noticing that this is a cubic, and I've just done a cubic, which would be boring. So we're going to make this 4th degree instead. We'll make it a quartic. So let's think about functions. If I have x, I don't have any turning points, it's linear. If I have x squared, I have some kind of parabola, I have 1 turning point. If I have x cubed, I have 2 turning points. When I have x to the 4th power, I have 4 minus 1 or 3 turning points. 1, 2, 3. Some people have a hard time thinking about them as turning points, and they want to count like humps instead, and that also works. Like here's a hump on this one, another hump, that would be 2. This one has 1 hump. Our quartic has 1, 2, 3 humps. So it's always, if you take the power and subtract 1, that's how many of those turning points you have. Because this is a positive leading coefficient, though, my graph isn't going to be an upside down one. It's going to be right side up, just like parabola. So for a positive x squared, it's like this, and the tails go up. And if it was a negative x squared, my graph would go down. So anything that's an even power will follow that. So my graph will look something like this. And now I want to think about what's happening on the left and the right. What are the y's doing as I go to the left or go to the right? So the limit as x goes to negative infinity, that would be this part of my graph right here. So as x goes to the left, what is my y doing? What is my f of x going to be? Well, because it's going up, it's going to be positive infinity. And now on the other side, if I do the limit as x goes to positive infinity, that's this end here, what is f of x doing? And it's going up as well. So this one's also going to be positive infinity. So we have one last graph that we're going to try here. So we have a rational function here. These are good for us to practice. I know they come up in math a lot, especially as you work your way through calculus. So my strategy, I've already told you, with a rational function is always to factor first. So let's see, I could factor this to, let's see, negative 2, so x minus 2 times x plus 1, and let me just check that. Negative 2 times 1 is negative 2. When I add them, I get negative 1, so that's good. So I need to kind of go through and do some graphing steps here. So my x-intercepts always come from the numerator equaling 0. So I will take x plus 2 and make it equal to 0 and solve. So I have an x-intercept, x equals -2. I can find a y-intercept by letting x equal 0. I've always found them that way. So f of 0 means I'd have 0 plus 2 over, I think I'm going to use my original form, not my factored form. 0 minus 0 minus 2. So 2 over -2, which is -1. So there's my y-intercept. So I'm getting there. I also need to know my vertical and my horizontal asymptotes. So my x asymptotes, so that would be vertical. Those come from my denominator equals 0. I'm not going to have any room for graphing by the time we're done with all this math work. So if I have x minus 2 times x plus 1 equals 0, that means either x minus 2 is 0 or x plus 1 is 0. And so my values for x are 2 and -1. So now I need to worry about my y asymptotes, or my horizontal. And for those, I'm always looking at what degree I have in the numerator and denominator. So I have a bigger degree on the bottom. My denominator is squared and my numerator is just linear. So because it's bigger on the bottom, I know that it will be automatically y equals 0. So now that we have all this information, we're going to put it together. So I'm going to go ahead and draw some axes. And I'm going to plot the stuff I have. So I have asymptotes. Let's start with my asymptotes. So I have a vertical asymptote at 2. All right, I got that. I have a vertical asymptote at x equals -1. Okay. My actual x-intercept is at -2. So let me make a point at -2. I'm going to do my graph actually in red, I think. And then my y-intercept is -1. And then my y asymptote is y equals 0, my horizontal or my y. So we know that we are not allowed to cross vertical asymptotes. And we know that we go through these, we know we go through the intercepts and we can get really close to those asymptotes, but we're not going to cross them. So we can kind of tell this middle part of the graph goes like this. I said I was going to do red and then I forgot. That looks pretty logical. And then what I see from graphs is they're always kind of alternating. You know, if you have part of your graph up here, then it'll be here, and then it'll be here. That's just a pattern that I've noticed. And you get this by just graphing a lot. So what you can also do is just make a table and do a couple values, like to the left of that vertical asymptote, between them, and to the right of the last vertical asymptote. So you can do some test points. But I'm pretty comfortable knowing that I have this point here and that I have the graph right here. I'm going to go ahead and put part of my graph on this side because I know that they're going to alternate. And then this one's kind of weird. It's going to have to cross that in order to have that point there. So we're going to make it go really close to that asymptote and then up. And I feel like this is really wobbly, this stylus today. So I wish that the graph could be a little bit neater for you. But I do hope this gives you an idea. These rational functions are something that we just need to be practicing a lot and probably every single day so we get the hang of them. There's a lot of different graphs and it's really through confidence and experience. So there's no easy, quick, dirty way to learn these. You really have to do all these steps like we did and just practice, practice, practice. Now I feel like the whole point of this was not actually to graph it, but to come up with those limits. So when I look at limits, I want to go to the far left and the far right. So I don't care what's happening in the middle with the asymptotes. When I'm looking at the left, I'm looking at over here. Where is my graph going? So my limit as x goes to negative infinity of f of x. So this one's weird. It gets closer and closer to the line. So we're going to say the limit is 0. It's approaching 0. And on this side, the limit, I can tell too, the longer I write on this surface, it doesn't get very neat anymore. As x goes to infinity of f of x. Same thing here on the right. This one's going to 0 as well. It's getting closer and closer to that y equals 0, that asymptote. This is the end of our 1-3 notes. Have a great day, and if you have any further questions on any of this, please ask your teacher. Thank you.